Hello there. Welcome to a Sunday morning if you're in the same time zone as me, or a Sunday evening if you're farther along in the future than I am. Apologize for the technical details. Keys tend to rotate and the stream wasn't connecting, so I'm glad you folks are here. I think we have about 10 people in this live stream, so if you're here, send me a quick chat. Let me know if things are working. I'm looking at the settings and everything seems like it's fine, but with these live events, you never know until the final thing. All right, seems like somebody can hear me. Good morning, Chad. Good to see you. All right, so with that, let us not delay any further. Let's just jump right into it. We're going to switch over to our slideshow. So today we're going to do another slideshow. It'll be, let me turn the capture card on so you can see me. So it'll be another one where I am talking to you. So far these have been good, but in the future I'd like to do something more that's a little more interactive. So we'll talk about that more in the in the presentation as we go. So just maybe quick show of hands or in the chat message. Let me know whether you read this chapter and where we're at, or whether you're just joining in for the first time, so we can get a sense of the audience here. While I pull this up. And I'll take a little moment to talk about Ljubljana, which is here. This is Paidita Ljubljana invited me to talk, and I really liked actually their landscape and their city, so I decided to use them. Okay, I see that Julio has read it, so and Chad. Okay, great. So we have 2 people that have read this chapter. That's really good. It means we can have a pretty good discussion. Everybody read this chapter. Okay, this is actually really great. I'm glad you folks jumped into it. Dang, a lot of you folks are studious readers. This is going to be quite the fun book club. So, agenda for today, another welcome back. I'm going to take you through a tour of the discourse. I got some feedback that it was a little confusing what features are available and where to chat and where to meet people. So I want to just talk through that and show you what's there. The discourse is really important because this is a book club, not a book lecture, and we've been having some really good discussions in the book club. So I don't want anyone missing out if they don't know what's there. We'll go through the chapter overview and then even some challenges that we had when reading the chapter that other folks had noted and I myself had seen. I'll go through a little bit of the discourse, and then we'll talk about something about causal inference in real life, and we'll try and do another live Q&A. So let me show you through the discourse. If you have not already seen this, or this looks entirely new to you, that is a problem. So what you're going to see here is my discourse. I have a lot more going on my screen because actually this is both the discourse for the intuitive base course and the book club. What you folks will see likely is this causal inference book club category right here. So when you click into here, you're going to see a whole bunch of topics. These are all just the various threads of conversation that are in here. Here's one where somebody had a question about chapter 2 and frequential statistics, and there's a whole discussion. So you should feel free. Actually, it is encouraged to go in here and post topics about whatever you're thinking about. In here, there is a general category. So if you just have something that doesn't fit within the bounds of a particular chapter, then post whatever you like here. And then we will also have categories for each chapter as we go through them, so we can continue discussing as we read through the book. So these are all the discussions for probability and regression review, and quite a bit of views. The introduction chapter didn't have quite as many, but we had a couple. And then the next one that's coming up is the DAG, Directed Acyclical Graph chapter. So that's the probably traditional forum that you've seen. I thought a forum would be really good for this particular book course because we're trying to capture knowledge, and Discords tend to be high velocity, which is great and exciting, but then all the knowledge gets lost. So in the spirit of us learning and retaining knowledge for a long period of time, not fleeting information that excites us in the moment in our short-term memory, but then gets lost, that's why we're using a discourse. The one other feature though, is there is a chat. So if I pull up the chat window, you should all be able to join the Causal Inference book club. So if you like more of a chat atmosphere, I know right now we have the YouTube chat, but outside of a live stream, if you'd like to have a more casual chat or have a quick question, all of you should be able to join this Causal Inference book club chat, and then have a quick conversations here as well. And then if things become if things become more becomes like a bigger discussion, these can be moved to topics. So hope this provides a good balance for the community. I will also post a quick tutorial on how to find these in the discourse. So hope to see folks utilize that as well in their learning. All right, back to the slideshow. So like this, we will learn more effectively if we learn together. Sharing ideas, actually a good way of maintaining your sanity is, somebody had noticed that there was a pretty egregious notation mistake in this chapter, in one of the first formulas nonetheless, and one of the most basic definitions of probability. And myself and two other people maintained our sanity by realizing this was a printing error and was corrected in the online edition. So with that, let's get into our chapter overview. Quick thoughts. I'm not going to talk through the details of every single thing in this chapter. It was quite a whirlwind of notation and basic probability theory, and then a lot of frequentious type statistics, and actually Bayesian as well. Shouldn't say that. There was a Bayesian section. And then regression. So a whole lot going on this chapter. I'm going to skim through the high points so we don't go through another basic probability lecture. This will be a very opinionated take on this chapter, so you'll hear a lot about my thoughts on this particular chapter, and I hope in the live Q&A we can get your thoughts as well, and then of course in the discourse. So for me, these were the three primary topics that I took away from this chapter. One was probability overview. I like to call this rules of the road for statisticians. We'll talk about that in a second. There was a section on inference. So both frequentious and Bayesian, although I'm going to put a caveat on Bayesian. For those who don't know, I identify as particularly Bayesian for a lot of reasons. It's been more useful to me, so we'll talk about that. And then regression, which is where we'll spend most of our time. I think the regression is going to be the topic that is continued most throughout the book. Again, I haven't read the book yet, so I don't know entirely how it's going to progress, but certainly regression seemed like, and as stated by the author themselves, regression was the tool that helped make causal inference. And the frequentist and probability were just in support of regression. And like every chapter, I'm going to post what I think is the most important figure from the chapter. For me, that was regression anatomy. And there's a I guess it's the subsection titled regression anatomy, and we had this plot of both the bivariate regression and then the multivariate regression for car price as correlated by these covariates. So with probability and basic summary stats, I feel like it's like a rule of law that if you write a book or have any lecture, you have to include either a Venn diagram of sets or the probability, the joint probability tree that you can see here. Scott Cunningham includes both. So if anyone has questions about basic probability, please ask in the chat. But I'm at this point, I think people have seen basic probability many, many times. But essentially, for me, we'll talk about this in a second on the next slide, but basic probability is sort of the alphabet of whatchamacallit, of statistics. And then there was also some basic summary statistics, so variance and mean calculations that were brought up. So you have some random variable algebra, and if you add variances together at the random variable level, that you can't just add them together maybe the way that most people would, but you have to do a little bit more and account for like the expectations and all that. So basic probability rules. Really good review of them, by the way. I actually really appreciated the depth that Scott Cunningham went into to explain it from scratch and bring it through each point in a condensed manner in less than half a chapter. So I thought he did a wonderful job. I also really appreciated him doing that, because for folks that pick up this book and don't have that background, instead of just jumping in to some sort of panel data discussion or some very theoretical discussion, he lays out the framework. Another reason that I really, really like this author's writing style, he acknowledges that not everyone has the same background, so he takes the time to lay it out and put these foundations in. So I thought it was quite excellent. Now for our discussion on probability, a big topic that comes up is frequentists versus Bayes, which we will definitely talk about in the next couple slides. But I think what happens, and it actually happened in this book as well, is that nearly every textbook starts with a discussion of probability and moves straight into frequentist statistics, but usually shows a thing about Bayes' theorem, and it's unclear how these three things relate or what's going on. So for me, this is the way that I like to think about it. It took me a while to get here, so maybe this will be useful for you. I like to think about basic probability as alphabet. So all these symbols are just letters, right? They're I, B, N, S. If you're speaking English, which we'll assume, or maybe even a couple other languages. Well, let's just assume English to simplify this metaphor. We just agree that this sounds like an N, this sounds like a D. I know English is weird and vowels change sounds, so let's ignore that again for the sake of the analogy, but T sounds like ta and it's written like this. And then you can take these basic letters and you can put them into words, which again are just uncontroversial. So you could say Indian or food or is. These are just constructions of the alphabet, and they're not all that controversial, and everybody agrees with them. Whether you're Bayesian or frequentist, we all agree that this is how probability works. You can even see sometimes we make mistakes like the author did, and we make typos, but nonetheless, these are all letters, and nothing is controversial here. There's no difference in opinion. Now, what happens, though, is when you get from the basic rules to inference, which is where people disagree. So, based on my life, I've inferred that Indian food is the best. Nothing has changed here in the terms of the letters and the words. You still have letters, you still have words, but now I'm drawing a conclusion about something that I believe about the world, and some of you may disagree that Indian food is not the best in your experience. Your random sample and your upbringing of foods have led you to conclude that maybe Mexican food is the best, or Italian food. This is what I think of with frequentist and Bayesian statistics, is we all agree on this portion. Again, Bayesians and frequentists will do the same thing with point probabilities and with measure theory. But when it comes to the philosophy of randomness, that's where we diverge. So there was actually one line in the book that said this, that we need to build up the justification to capture the inherent uncertainty in the sampling process itself. The Bayesian statisticians would say we want to capture the inherent uncertainty in the parameters of the model. And that is the key difference between the two philosophies. And just that one thing is where everything diverges, and all the math and all the derivation and things end up being different. But I just wanted to point out here again, I feel like this is not well covered in a lot of textbooks, and this is a crucial difference. And this will continue to be a crucial difference in this particular textbook. Again, because I've now come from a very Bayesian bent. I really use that particular philosophy. because that's the one that works well in my line of work. But that doesn't mean that either of the two are wrong. They just now, because they go down different paths, have different derivations and different assumptions and different math and different plots and all of that. So I'm going to pause there for a second. I said a lot, and this is probably going to be a key difference for this book club in particular, and also your statistics learning. And I'll take any questions. I think the live stream lags about 10 seconds, so I'm going to wait quite awkwardly, and then we will continue on. I'll say, going once, twice, thrice. Don't know the words for fourth and fifth, but I don't see anything coming in. So let us continue then. So a couple notes on the Bayes versus frequentist. I want to point out that there should be no argument in this book club about which one is better. There should be no, I'd say, biased argument about which one's better. Certainly, let's discuss and let's talk about it. But I think the key thing is learn both. Just take it from my career. It's good to learn both because there's going to be Bayesian analysis, there's going to be frequentist analysis. There'll be great work in both paradigms. It doesn't mean that you should not understand that work. It's still principled. People are still trying to draw conclusions with data, and that's what's really important. In terms of this book, there was an example on Bayes' theorem. I wish it was better. So if there's a way to teach Bayes' theorem with point probabilities in sort of constrained worlds, so the Monty Hall problem that you saw in this book is, let's say, a constructed world where it's a game show and there's only a certain fixed number of actions that could happen. And with that, you have point probabilities, and then you can form a conclusion about everything. That is certainly one way to use Bayesian inference, but there is a world of ways to use Bayesian inference, from the way I use it to plan rocket supply chains, to medical discovery, to coal mining disaster changes in legislation. And if you haven't used Bayes' theorem in that way, I would encourage you to do so. It's quite an amazing use of statistics in my opinions. I also recorded a full-length video on this topic that you folks can watch if you are more interested in my thoughts on this. I have posted that in here. So there's a full video I created on this topic. It's about 15 minutes. I didn't want to take up the whole live stream today speaking about that, but check out this topic. You can watch the video and feel free to ask as many questions as you like. So for the most important topic in this chapter, it was certainly regression. So it was the first applied example that we had in this book. I'm particularly biased towards applied examples in my own learning. I find that when I start with theory, things tend to be very abstract, and I can't really keep it all in my working memory or place connections as to what's happening. But if I see an example and I understand the endpoint and work backwards to the theory, then I understand the linkages of how to go from the desired end result to what all the supporting foundation is. And in this book, this has been the first applied example. So it's the first one we saw where math and code were used in something that is, in my case, tangible, car prices. He showed a bivariate regression here and then a multivariate regression. So there was quite an important point here about if we want to understand at this point the correlation between length and car prices. If we just take length in and of itself and then run a regression against the car prices, we end up with one slope. And then if we take three other additional covariates, in this case weight, headroom, and miles per gallon, the trend actually shifts. And he makes a big case here about controlling for these variables, and it'll be natural to control for these variables. This is a topic that's going to come up over and over again, especially if you use regression, that the model covariates will change depending on what you include. And in this book, he uses the conditional expectation function to describe this in great detail. For an additional analysis, I had redone this in might already have this. I had redone this in Bambi, which is a Bayesian wrapper to PyMC, and so this is the same regression done in Bayesian stats. The Bayesian stats portion isn't important, so much so that the estimated parameters came out to be quite similar. So if you want to see this, go to this notebook, and I have all the details there. What's important, and I want to make this distinction clear as well, that there is a model of things that is independent of what estimation technique you're going to use. So we have a model, and we say that in this model, the only thing that we care about, the only thing we identify that affects prices is length, and right here. And we're going to regress just on length, and there'll be some noise, but just length is the only covariate we're going to use. That's the model, and we see this particular model has three parameters. Now, how we're going to estimate those parameters, it can be done a bunch of ways. You could do it using, honestly, random guessing. You could just randomly guess what parameters are, which is not an advisable technique. You could use ordinary least squares regression, which will get you the mean of the parameters with least squares fit, as the name implies, but not the uncertainty. Or you could use Bayesian estimation, which will get you both the mean and the distribution. In the book, there was actually, I think this was another nuance that could have been explained just a little bit better, but ordinary least squares regression is the estimator for the mean of the regressor, just the line, so just this middle portion. And then the frequential statistics are what helps you estimate the uncertainty around the parameters of the model. So you now, in the book, you now know the mean of the length covariate, but you may want to get the uncertainty of that mean estimate. And because this book uses the frequentious paradigm, it uses a resampling method to then get that histogram. And let me pull up that plot so this isn't so abstract. While I'm pulling this up, I have a question for you folks, because I'm always trying to learn from your feedback. Let me know if this is the right level of the discussion, or whether you'd like to move a little bit more high level, or want me to dive in a little bit deeper. I could go either way. While I wait for the live stream to catch up for you, let me show you. Here we go. All right, Jay Collins loves it. Okay. So in the textbook, he shows, I think this is the right one. Is this? There's a couple of uncertainty plots, and this is the right one. Okay. In the book, because the book uses the frequentious paradigm, it uses, this is the way that uncertainty is estimated. Let me find, there was a particular line. All right. Here we see the estimate of the mean value from coefficient from repeated sampling, and this is the idea, and this is the way to get parameter uncertainty estimates in frequentious paradigms, which is repeated sampling. So this is the way the book did it. This is the way, and this is the way that Bayesians do it. We don't do repeated sampling, but we do likelihood calculations. Again, I'm going to write this down because this point is so important. Let me just add a slide here. Where do I want to add this slide for you folks? Let's just add a slide right here, and we'll just type it out. I can't add a slide because this is view only. All right. And I don't have mouse point. All right, we'll use VS Codium, and I'll just write it. I'm going to write this out just so it's really clear. I'm really winging it at this point, so. All right, text file. Okay, so that is not what I wanted. I wanted a text file. Okay, so there's three things. There's the model. and this could be a linear model. This could be any other sorts of model. What other model? This could be, there's things called SIER models, which are used for like COVID disease estimation. This could be an exponential model. It doesn't really matter. There's the model and model set parameters. That's point one. Models define parameters. And then there is parameter estimation. And so you set a model, and then you set a parameter estimate. Or sorry, you set a model, and then you estimate the parameters some way. And you can estimate the parameters using frequentious methods. Okay, actually, let me point out two things. Now in the parameters, you can estimate the mean of the parameters. That's one thing you could do, and then you can also estimate the let's say the variant. I'm going to call it uncertainty. The uncertainty in the parameters. In the book for regression, OLS is used to estimate the mean, and then frequentious methods are used to estimate the uncertainty. The reason I'm bringing this up so deeply is that most of this chapter is dedicated towards proving that these estimators are unbiased and meet a number of conditions that he lays out in the book. So if you were curious about all the math or wondering why he was defining so much math, he did a really good job explaining the features that we would want from our estimators, so that we would want them to be unbiased, that we would want them to meet some of these like conditional expectation functions. And then he showed the math of how to make this possible. And then towards the later end of the chapter, Scott showed if you relax some of these assumptions, like you relax the homoskedasticity or heteroskedasticity assumptions, or you relax the independence assumptions with the cohort regression, how those estimators would work. That was the point. That was the bulk of this chapter, and I think what was most important for us to take away from it is that the properties and the assumptions under the estimators, and he showed that all for frequential statistics. And for me, I don't know how much I'll do this in this book, but I again reanalyzed these using Bayesian statistics, and I can't go into a whole comparison here, but it's the exact same idea. We have the exact same model, whether it's the bivariate regression or the multivariate regression that you see here, and then we use Bayesian methods to get estimates. This plot is wrong, so ignore that. But we use Bayesian estimates to get the intercept, mean, and uncertainty. So this is the point. Bayesian estimators do both at the same time. I don't want to say frequentious estimators do one each, but ordinary least squares regression does one, and then frequentious statistics does the other. That is my point on what this chapter was about. Again, the reason I went into it in depth is to explain what the basis of this chapter was. Let me read the comments real quick. Ben asked a question about Bambi versus PyMC. I'll answer that at the end, Ben, but I won't forget about it. Does unbiased means not different than the population value? So like statistics trivia. Let's see if I get this right when I say it off the top of my head. I'm going to give you what I have in my head, which might be wrong, but I'll definitely also post a topic. In statistics, unbiased means that if you have a sample that eventually, as you get more and more samples, your estimator will converge to the true value. So a biased estimator of the mean would mean that if you were performing estimates of the mean from a sample, even as you increase the size of the sample, it wouldn't converge to the true population mean. That's what a bias would be in a particular estimator. In frequential statistics in particular, you see this thing called like unbiased standard deviation, and then there's like biased standard deviation. So I'll just drop this in the live chat. There's a lot of theory in math about unbiased versus biased bias corrections, and you can see this all here. So good discussion for the discourse. I encourage you, Ambika, to post a question, and then the whole group can bring it in. All right. So with regression, the good news is with simple regressions, both frequentious estimators and Bayesian estimators tend to converge to the same value. In the live stream, in the video that I recorded about the difference, Jake Vanderplas goes into more detail about where sometimes the two diverge. But it seems like for the purposes of this book, especially because we're using regression, whether we use Bayesian methods or frequentious methods, if we're starting with the same model, we'll end up with very similar parameter estimates. So what I want to point you to is two other resources. If this chapter was really interesting to you and you really enjoyed the details, let me turn the capture card off. You really enjoyed the details of how to go from probability theory all the way through these properties of estimators and how they work. These two textbooks I find are quite good. These would definitely answer some of the questions that I'm seeing in the live chat. This particular book, Understanding Advanced Statistical Methods, does a great job of going through both paradigms. Actually, it starts with probability theory, and then over 20 chapters, it builds up to the Bayesian statistics and frequential statistics. It talks about biased versus unbiased and all of the details thereof. And then if you're more interested in a Bayesian regression mindset, regression and other stories, also does a fantastic job starting from the basics and then working through Bayesian regression. There also is the whole causal inference series of chapters in this book. I think actually 6 chapters. So a question I had for you folks, let me turn my camera back on, is that maybe at the end, if we enjoy causal inference so much in this book, maybe at the end we could go through the 4 to 6 chapters, I believe, in this book on causal inference. If it sounds interesting to do sort of a causal inference addendum with another textbook, let me know, and I'll start planning out the logistics to make that happen. So in every chapter, I try and pull out the one quote that I think will be the most important moving on. And in this particular chapter, there was one line about the mean independence relationship is crucial for the intuition of the parameter beta 1 as the causal parameter. And so I think regardless of whether you're using frequential statistics or Bayesian statistics or whatever it is, this idea of mean independence is the way we're going to be able to identify things as the causal parameter. And I think as we go later on in the book, we'll continue to see this come up over and over again. So again, what we're trying to learn here is causal inference in practice. And so these estimators and frequentists and probability theories, they're all tools in service of us being able to make a causal claim, which is really, again, the thing that we're looking for here. Not that we have a bunch of math, but at the end of it, we can have, we can say something about the world and the way the world works so people can make better decisions. I'm going to pause here again for a couple of questions before I actually take a short detour to talk about causal inference in practice. So I'll do I'm going to do my counting again because it helps me actually learn how long this takes. So 1 1,000, 2 1,000, 3 1,000, 4 1,000, there's some water, 5 1,000. Very dangerous. I see a couple of questions. Does biased versus unbiased have to do with degrees of freedom in the SD calculation? I think that's maybe the most famous example of biased versus unbiased estimators. It's the one that early statisticians tend to see the most. So yes, the degrees of freedom, let me put the full cam. The degrees of freedom is one place that you see it, but it's an important property of estimators to show whether they're biased or unbiased. So an example from the Bayesian context, by the way, is I'm going to go into a really deep topic here real quick, throw it at you, is there's this famous example called the 8 schools problem, which is a common Bayesian example. And if you write your model in, let's say, the most intuitive way, what's called with a non-offset parameter, you end up with a biased estimator of the mean. But if you formalize it in another way, you end up with a non-biased estimator of the mean. If anyone's curious about that 8 schools example, Michael Betancourt has done a really good example showing with a bias, and I can pull that up at the end as part of the live Q&A. But this biased idea is something that applies all through statistics, and this degrees of freedom in the standard deviation calculation is just one area that you see it. Annie says, I read the estimator for variance of the sample is unbiased estimator for the population. However, this does not apply to the standard deviation parameter. I'm going to believe what you read. I'll be honest with you. I often forget all these probability rules. This is a whole other thing I'll talk about. But when I go to interviews for companies, I tend to have to refresh my memory of all these details because I don't remember how to derive them off the top of my head. I usually have to end up going to references to remember the details of each one of these, and I sort of just remember in my head where the pitfalls lie. Maybe that makes me a bad statistician. Maybe I shouldn't be admitting all this, but this book, for example, will be a new reference for me. If I ever have to understand how frequentist regression works and the assumptions, I'll be using this chapter as my refresher whenever that comes up for me in the future. Lars says n-1 is correction for the variance estimator. I think NumPys don't include it, but I'm not sure. Lars brings up a really good point. Actually, this is commonly a very confusing thing because statisticians do it both ways and different people do it different ways. Where is it? In the slide deck. So this is the slide deck for the video, my Bayes versus frequentist video. And I can just show it to you here. So here it is right here. So here is the calculation done using NumPy. It does it one way, but then in SciPy, you calculate degrees of standard deviation. It does it a different way. So you have to just be careful how you do this. So here you can see that in one method, with NumPy we have to apply the degrees of calculation difference. This actually defaults to 0. You can try it out yourself. If you use SciPy, it implicitly makes the difference assumption and you get it there. I am not showing my screen. That is really embarrassing. There we go. Sorry about that. Thank you, Surya. So there we go. Different libraries make different assumptions about this degrees of freedom. What I would say, again, my takeaway for this chapter is get a sense of what's going on, understand that these estimators are the ones that help us estimate the model, but and then refer back to this chapter. But otherwise, this ends up becoming a whole what ends up happening, I realized, is we get sidetracked on the theory and then we rarely get to the actual applications and the problems. So I'm interested to see in the rest of this book whether it'll continue going back to the theory or whether we'll start moving into more of the causal inference ideas. But again, being a probability and regression overview, there was no way to avoid it for this discussion. I'm glad you folks are all asking. Okay, so let's go to maybe the next thing that I had. It's outside of the book, but I admittedly am going to be honest here and tell you I was very distracted the last 3 days about a bunch of things that are going on in my particular country, so I didn't get as much time in my head to put together this book club the first couple of days, but then I realized that there was an important connection. And so it has to do with causal inference and women's rights. I am very just bluntly going to say this and not dance around this topic. As somebody that is an American citizen, I am extremely unhappy with the way the Supreme Court made the decision a couple days ago. And that is my personal feeling. And so with that out of the way, I'm going to then talk about at least the causal inference that came out of it. Of course, a lot of people have a lot of different opinions and ideas, but then also had different ways of engaging in the conversation. And in this particular case, there was a very large group of economists that used causal inference to talk about their research and their study. And I'm going to say this wasn't opinion from the economist side. This was them doing actual causal inference research. And they published a large PDF and sent it to the Supreme Court about causal inference confirming that Roe v. Wade changes the arc of women's lives. I think for me, this is the important part about this entire book club. Yes, there's the theory and the math and biased versus unbiased, and that is all important to lay out the agreements we have about the math. But again, for me, I really want to go through this book because I want to learn how to use causal inference to help make conclusions, and very informed conclusions about how something affects something in the real world. This being a particularly great example of a decision that is going to affect the lives of people in certain ways, and a rigorous way to make that claim. So again, this came from a group of statisticians that submitted this to the Supreme Court of the United States. I'll pull up the PDF in a second, but this paper by English and Pisk was mentioned in the chapter numerous times, actually. And it was mentioned in the book numerous times as part of the regression model. And then as I was reading this brief from these group of economists, the same thing came up over and over again. So again, a great example of how these ideas then get applied into really, really important discussions that have really big impacts on the things going around us. So let me okay, I have it right here. So if you would like to hear about this or read this more, there is quite a bit in here. There are plots. There's a lot of conclusions. I enjoyed reading it to get a sense of where I think we're going to go in this book. There are a lot of methods and things mentioned in here, difference methods and things like that. So regardless of your feelings on the matter, if you're interested in causal inference, this is quite a well done paper on causal inference from not just one author, but I think when I was looking at the bottom, hundreds of authors. And actually Scott Cunningham is one of the authors of this as well. So in our book, the same fellow that wrote our book also helped contribute to this paper. So with that, I should point out one more thing. There is an NPR podcast on this. NPR Causal Inference. It's a pretty short podcast, about 9 minutes. It's interesting to listen to because one of the authors of this paper talks about her work, and the way her feelings are separated from the math and the way that the math works out as facts. So, super advise going through this. If nothing else, it's a good context for how this math and all gets used in the real world. So for this book club, let's talk about what's next. First off, I want to say, again, we've made it now about 43 minutes into this. It seems like it's providing great value to these folks, and you're having a lot of fun. I'm having a lot of fun. So, if you have 2 lines, that's 2 points. You now have a line, and the line seems to be that this is great. It's hard to make any inferences when you have one single point, but you got 2 points. You got a trend. That's the whole point of this chapter, and it seems like we have a trend here that this is nice. So I'm really, really excited to keep doing this with you then. So for what's next, let's read. I messed up this. I should have. Sorry, I was very, very distracted the last couple of days. So I apologize for all the typos and the mistakes, but we are going to read the directed acyclical graph chapter by next week. So it's a smaller chapter. There's a lot less math in this chapter. For one, it's much more about collider bias and the way to draw DAGs and the motivation for DAGs. So you can take your math hat off and you can take your coding hat off, and you can put on your sort of like creative thinking hat more so when we go through this chapter on directed acyclical graphs. Let's read this by July 9th. That's in 2 weeks. So let me know if July 9th is too soon, either anytime maybe this week. If we have a consensus, we can push it out for another week. But I anticipate this being one of the easier reads since it's a shorter amount of text and it's not as math dense. I would also love to feature some of you in this live stream. So I would like to test out this technology or this platform called StreamYard, where one of you can come on and we can have a discussion, a live discussion. Even I think up to 7 of you could come on and we could have a live discussion. That way it's not just me talking to you the whole time through sort of one causal direction or one direction, but we can have a greater chat. So if that sounds interesting to you or you would like to be featured, let me know if you would like different formats, and then let me know if you would like to participate and be in part of this live discussion. I would love to get you in, get you set up, and get this whole thing going. Oh, Julio says 9th is a Saturday. Yeah, let's do the 10th. So let's do it on the 10th again. One thing I'll point out is somebody had asked whether we could change the time around. So I'm also another thing I'll do is post a poll of whether people would like to keep this time slot or whether they would like to move it around, so we can include anyone who's likes to join. Again, you need a little, like the last chapter said, the first chapter, you need a little bit of randomness sometimes to figure out what is causal or not. Right now, we've had no randomness. We've had the same time slot. So the question I'll have for you folks is, should we inject some randomness and see what happens, or should we stick with consistency? Always the key question. With that, I will open it up to a live Q&A. We had a number of fantastic questions that came up during the stream, and I want to maybe give us like another 10 to 15 minutes to see if anybody else has any questions on any topic. I'm happy to answer however I can. All right, so I see Annie has a note. The last note about variance and standard deviation estimator. Yes, n-1 is the degree of freedom adjustment to get an unbiased estimator for variance. I understand there's no such adjustment for standard deviation. For me, Annie, I always have to look this up. Honestly, I forget with this particular thing which one should I use, whether it's biased or unbiased. I'm also just going to bluntly say that this is only a problem if you estimate these things using the Frequentius methodology. If you use the Bayesian methodology, you don't have to worry about this. It always comes out. I might be quoting out, but I'm pretty sure the Bayesian estimation techniques don't have these sort of challenges. They just give you the unbiased estimator when you estimate them in a model. I will point out, though, that this doesn't mean that MCMC or some of these methods are unbiased. So you still have to prove that the Bayesian estimator is unbiased, whether that be the Laplace approximation or conjugate model or MCMC. In those Bayesian methods, each one of those estimators could be biased, but generally, especially for simple linear models, the Bayesian estimators tend to be like the MCMC estimators tend to be unbiased if you finite sample infinitely. If anyone's curious about Bayesian estimators, I can post something in the general topic about Bayesian estimators. I can also point you to my blog about biasness, about the various types of Bayesian estimators that are out there. So if you're curious about Bayesian estimators, here is an entire list of all sorts of Bayesian estimators. That was a huge digression. I know you didn't even ask that question, but now you guys get to hear about Bayesian estimators. Now you folks get to hear about Bayesian estimators. Do you have an intuition of when these regression anatomy plots are not a good idea? So I don't have an intuition of when regression anatomy plots are not a good idea. I actually want to show you something. Let me pull this up. I got my old copy of Statistical Rethinking here. let me pull up particular plots. So from every textbook I've read, and even my own experience, regression anatomy plots, as they're called in this particular textbook, are usually a good idea. I think it's this plot. Let me see if this is going to show up well. I don't know if this is even focusing, but I'll try and find this and post it. In Richard McElrath's book, Statistical Rethinking, this is the first edition. I have the second edition on my shelf. He also has what's called regression anatomy plots. And regression in other stories also has quote-unquote regression anatomy plots. So I'm seeing over and over again that, and even in my own work, that these regression anatomy plots are really good, and that I tend to always use them to help see what the difference is when you start adding multiple regressors. So in this textbook in particular, I'm actually really curious to see how regression anatomy plots are used later in this book to help make some of these causal claims. It's a point I'm very fascinated to see. Coming from frequentia stats, I had a tough time explaining degrees of freedom and why I shove an n-1 in any estimator to business folks. Yeah, I also have a tough time explaining frequentia statistics to business folks. It's actually one of the primary reasons that I actually is one. Yeah, it is a big reason I switched to Bayesian statistics. I have trouble explaining confidence intervals in a way that people get. So it's basically this. I have a really hard time explaining this plot, which is what a true confidence interval is, and I also have honestly, even in this book, when we had where is it? I want to show you the plot. It was these plots. I had to squint really hard to figure out what was going on in these plots. I know what he was trying to do, what we're showing, and I'm really glad that this was shown. Like, it's really important. But I also was like, it took me a while to figure out what was happening here and what was trying to be shown. But it's the same idea that 5% of these intervals miss the true population parameter estimate, which is the same thing that's being shown on this plot. So I have a really hard time explaining that. I have a much easier time explaining the Bayesian paradigm. Let's see. What are the questions? I remembered from way back that because you're using another estimator mean as estimator from you, so you lose 1 degree of freedom. Please explain this plot. Good example. So yeah, Annie, I have something. I remember vaguely something about that as well, that you have to make some correction. But I honest to God, I always forget this every time I go into an interview with a company, because I tend to use statistics. I've only really used statistics in industry. I don't have a stats master's or PhD. I have to study these things because it's one of those interview questions that comes up over and over again. So if you're going to interview for a company, I would suggest going back and reading these things in case you get asked this question. But when I end up working, I don't have this question coming up over and over again. Annie says, please explain this plot. Okay. I will do my best to explain this plot. There was 2 of them, actually. There was this one here, and there was the one over here. So, okay. Let me try and like prep my brain to remember how to explain this live. Okay. So let's start with the easy point. We have a true estimate. We have the true population parameter, which is 0. And then it's, because this is shaded in like so strongly, it's hard to see. But what we have here is we have a bunch of, if you randomly sample from like a distribution, sorry, if you randomly sample as he has here, I'll use the Python. Actually, this Python code is really long, so it's hard to show in here. But if you randomly sample a whole bunch, let's use the static. Oh man, even the static code is long. I'm gonna show it in my code base. Okay, here we go. If you randomly sample 100 times of, like, let's say a sample size. So what this particular line of code is doing is it's taking a normal distribution that's standardized with mean and standard deviation, and those happen to be declared up here. Where are they? Where did I put them? Not those ones. Here. If you take a mean of 2 and a standard deviation of 1 as fixed parameters, and then you randomly sample a sample size of this case, I think I did 16, but you do that 100 times. So you 100 times randomly sample 16 observations from this latent distribution, which has a mean of 2 and a standard deviation of 1. And then what you do is you take the mean of that, mean of all those 100, so you end up with 100 means, and then you also calculate the standard error of the mean 100 times. You will end up with 100 different intervals. So you have some theoretical distribution that is fixed with fixed parameters, and you have observed samples of that theoretical distribution, and you have 100 sets of those observations of that theoretical distribution. If you calculate the mean of the observations and the standard error of the mean of the observations using the frequentious estimator, you will end up with a bunch of lines, like these bunch of intervals, like this one here. And then if at the 95% confidence, if you have a 95% confidence interval, 95 of those intervals that are mean estimate with variance will include the true mean. In this case, in my example, the true mean was 2. 95 of them will include that, and 5% of them won't. That is the frequentist. That is like the very, very verbose, but I believe precise way of a frequentist of stating what the confidence interval is in the frequentist paradigm. So I'm going to pause here. Does my plot here make sense with the colors before I move on? I'm sorry that was hard for me to say. There's a lot of words and I got to get them in the right order. I'm going to pause here for like 3 seconds. Going once, going twice. Okay. So Ambika says the sampling 100 times never happens in real life. I'm going to point out this is literally the reason I became a Bayesian. I was working at SpaceX, and what I needed to do was figure out if a rocket part was going to be late or not. Like I honest to God, just needed to know whether like this engine was going to be late, because if this engine was late, we can't launch this rocket to space. And it like the conclusions I could make with frequentist statistics for a number of reasons were like I could not do it. So I could not make normality assumptions. There was no normality assumption I could plausibly make at all with my rocket lead times. I also didn't care about the mean of like 8 rocket lead times or 16 rocket lead times. So maybe in my case, I had about 18, I think it was like 16 or 17 samples of like this engine being delivered. I don't care about the mean of those 16. I need to know about the next rocket engine delivery. So I couldn't use that. And then I couldn't go in and be like, well, if we theoretically had 16 deliveries 100 times in the future, 5 of those would have a mean that was on time or late, but 95 of those would have a mean that's like this. That like was not at all what I needed to make a conclusion about. What I needed was this plot, which it's now taking me 3 years to figure this out, but I needed this posterior plot of individual observations and what the likelihood that individual rocket engine lead times would be late would be. This is why I'm Bayesian. This is not to say that frequentist statistics is not useful. I want to bluntly say there's an entire paper here where a group of economists use frequentist statistics to make conclusions about the mean of teen motherhood and teen marriage and all that. Super good, great work. I mean, again, really, really useful stuff. It just didn't work out in the situations that I worked in. So you ended up... I was trying to avoid this. I was trying to avoid getting so into this, but of course you can now see how into statistics I am now. So anyhow, that was my plot, and that was my total tangent into Bayesian statistics. If we go back to the book, what the plot was showing here is the same thing. This plot is showing that you have a true population parameter of 0, and in the random sampling, the random sort of like bootstrap style sampling that is done in the book, all this in light gray is the confidence interval, including the true population parameter, and all of these open darker dash bars are the ones where it was missed. So these intervals missed the true population parameter. These intervals missed the true population parameter, but these intervals did. This plot and my recreated plot here are the same. The difference is that Scott had he had sorted them, and so it creates that like smooth line. I left them random to make it more clear that it's these are random. There's no implicit sorting to each one of these. They're literally just random, and they're not ordered, and there's no ordering that is meaningful. This is actually what confused me about this plot. I was like, is this a logistic regression that's going on? Like, what is happening here? But I realized it's not a logistic regression. He just happened to sort the simulation, so it feels like there's an implicit order, but there's not. What just really matters is that these bars don't cross this line, and that these lines don't cross this vertical line. Whew, okay, we made it through that. So the big question, does this plot make sense now that I've gone through 5 detours and two explanations of this all? Maybe 3 explanations. I lost track. Are you confident in what this plot means? Does the interval of your confidence, on average, cover that the true parameter is this? The theory says that 5% will not cover the true mean, but bootstrapping you showed 9%. Yeah. So the thing is, Annie, is you have to do this an infinite amount of times, right? Like that's the hard part about statistics is that if you ever take a fixed size, a lot of these things kind of fall out. So I believe the interpretation is if you do this resampling an infinite amount of times, it will converge to 5% and 95%. It's very, very similar to the assumption made in MCMC that if you take an infinite amount of samples with an infinitely long chain, you will eventually converge to the true distribution. It's like a thing with statistics. What I invite you to do, and maybe I actually want to leave and I actually have a question here. If I included like some sort of like challenge or exercise or like take home at the end of each chapter, like an exercise that I think would be useful, would you folks find that useful? The reason I say that is maybe one exercise you folks can do is take my notebook here, and run it and run this 100 times. Run this. Set this to 100. Set this to 1,000. Set this to 10,000 or 100,000, and see whether you converge to 5% not covering the true parameter and 95% covering the true parameter. Okay, let's make that the exercise for this particular chapter then. I will invite you to go through this notebook, and in particular, let's rerun this so we get a sense of what confidence interval truly means. The reason I bring this up, by the way, and I don't mean to harp on this point, but the reason it is really important is it feels like in this book, again, not having read it all, but it feels like the amount of depth that Scott took to explain, where is it? The amount of depth that he took to explain this here gives me a really strong sense that later on in the book, we're going to be making causal claims about significance and non-significance. And they're going to come up over and over again, that there is a significant relationship between price and length of cars once you control for these other things. So there's not a significant relationship. And we have to be really good about understanding what he's saying and what that means later on to make these causal claims. I don't know for sure, but I have a feeling that that's going to come up over and over again. So I'm glad that Scott went through so much effort to explain all of these things, from the basics to conditional estimation to what confidence interval means. So later on, when we're making conclusions in the book, we know all the theory that goes into it. Cool. There's one other topic I wanted to bring up, and I apologize. I again got distracted earlier, and I didn't get to bring it up. But at the end, some of these last chapters bring up this thing called cohort. Let me find it. Like cohort regression and robust least squares. What did he do that? He talked about. Give me a second to see if I can find it. Cluster, you call it cluster regression. Okay, so I don't know for sure, but I want to point out something. I believe that cluster regression is very similar to a concept called hierarchical linear regression that is very, very common in Bayesian paradigms. So it's the question is, when you have groups of people, like let's say, okay, a good example would be going back to the abortion example because it's top of mind for me, that you'll have a cluster of people that are in California, and you'll have a cluster of people that are in Arkansas, and you'll have a cluster of people that are in Minnesota. What we don't necessarily maybe want to lump them all together, but because there's a cluster, there's extra information that we could utilize in our parameter estimation that either violates the assumptions that were made earlier in our regression, which is something that he brings up here, or can provide us a way to make estimates with like potentially less noise or variance or things like that. It's called cluster regression in this book, and we can see that here. I believe this is very similar to hierarchical linear regression. I don't know for sure. I didn't get time to dive into it thoroughly, but I'm likely gonna talk about it in the next chapter. So there's a chapter in my book about this. So if you would like to do a little bit of extra reading and this may be interesting to you, you can scroll through my textbook and maybe just even you can ignore the words and just look at the pictures of unpooled regression, and then pooled regression where parameters are shared, and then hierarchical regressions that have hyperparameter distributions. Is cluster regression the same as linear mixed effects? I'm going to take a rain check on that question because I always mess up the mixed effects things. I actually want to point you to I'm going to point this out. Gelman wrote a really interesting blog here about why he doesn't use the terms mixed effect and random effects. So I'm gonna leave this blog post here that it's hard to answer this question because people use the words differently. So actually, honestly, just based off the question, and what's in your head for linear mixed effects, I don't know. Maybe what you can do, Surya, is post in the discourse about your definition of linear mixed effects from whatever your background may be, and then we can see how that definition matches up with what's in the Causal Inference Mixtape book, and then what's in at least what I have in my book, or whatever definition we're going to end up using. Gelman also has a really good breakdown of this in his book Regression and Other Stories. So again, if you're interested in this topic and really interested in the regression and probability type stuff, super recommend picking up this book for regression, especially for Bayesian regression particularly, and then this book for both. All right. I see the view count is dropping off a little bit, so I don't know if folks are out of time, but let me know. Would you like me to keep answering questions? Do you have any others, or do we want to call it a day? I will leave it up to you. Yep, Gelman also uses a Bayesian approach for solving hierarchical models. Yeah, Gelman is unapologetically super Bayesian. He's definitely one of the leaders of the Bayesian inference field. He puts out tons of research and leads the STAN team and things like that. All right, it seems like we have a pause. No other questions. If you have any, drop them in the discourse chat. So feel free to go here. You can use this chat. You can also just post questions in the discourse. Very excited again for what I think was quite another fun day of discussion. I appreciate you folks asking questions and being so engaged. And I'm having quite a lot of fun learning with you all together, much more than I would independently. So with that, I hope you enjoy your next 2 weeks. I hope to see you on discourse, and let's certainly keep this going. Bye-bye, folks.